Welcome to lab number 10. In the last 3 labs of this semester, we're going to be dealing with bioelectricity and some electronic circuits, starting with this week's lab where we will model an RC circuit, and then the last 2 labs are checkoff number 3 and checkoff number 4 of the major project. The circuit that we're going to analyze in this week's lab is a resistor-capacitor circuit, or RC circuit. To get the model, you will download the file titled rc1.slx from Canvas. Put it onto your computer, and you can open it up in one of 2 ways. You can double-click on the icon on your computer, or you can open up Simulink in the MATLAB desktop, search for the file, and open it up that way. When you open it up, you will see the following model. It may take a while, it may take a few seconds for it to download Simulink and to open up Simulink, but this is the model that you will see. Oh, incidentally, remember that if the figure ever changes size and you need to restore it, go over to the left column and the 3rd button down from the top. Click on that and that will restore the view back to full size. Let's go through the various components. Here's the resistor in series with a capacitor. It is being charged and discharged by a voltage on the left side of the resistor, V sub S. And V sub S is not a constant voltage like a battery, but rather it's driven by a pulse generator. And the pulse generator changes from a high voltage to a low voltage. During 250 milliseconds, the output voltage V sub S will be 7 volts for 250 milliseconds, and then it will drop down for the next 550 milliseconds to 0 volts before it repeats itself cyclically. Notice that that timing is identical to the timing we had on the Wiggers diagram, because this pulse generator and voltage source Vs will be the pacemaker that will drive our left ventricle in next week's lab. Now off to the right are some measurement devices. First, we're going to measure the voltage on the top plate of the capacitor using a voltage follower and a voltage sensor. Why would the voltage follower be needed here? We do not want this voltage sensor to draw any current off of the capacitor during the measurement. It would perturb the measurement of that voltage. So we put a voltage follower in place. The output voltage is the same as the input voltage for a voltage follower, but the input impedance is infinity. And so it will not take any charge, it will not perturb the charge on top of the capacitor by the act of measuring that voltage. The voltage is measured with this voltage sensor and is put on channel 1 of an oscilloscope that will give us the time waveform of the voltage across the capacitor. On the 2nd channel of the oscilloscope is imposed the voltage from the pulse generator. It comes from this port directly over to this port. So the 2nd channel on the oscilloscope will show us the voltage that is being imposed on the left side of this resistor. Now before we do the simulation, let's pay attention to a couple of items. The first is we need to change the value of the resistance and the capacitance to match the values on the schematic, rather than the starting values or initial values they have now, which are not correct. To change the value of the resistor, you know how to do that. You double-click on the resistor, and in the dialog box, you change the value of a resistance to 47 kiloohms over here. Hit OK to store that. I won't do that, I'll keep it at its original value. For the capacitor, you double-click on that, and in the dialog box, change its capacitance to 4.7 microfarads, not millifarads, but microfarads. Hit the OK to save that. And once again, I'm just going to stick with the original values. And then the second thing, we need to anticipate what the voltage is going to be across the capacitor, here at the top plate of the capacitor, as a function of time, during both the charging cycle and the discharging portion of the source voltage V sub S driven by this pulse generator. During the charging cycle, the voltage will be 7 volts on the left side of this resistor. On the right side, will be the charge across the voltage across the capacitor, which would be low because it hasn't had time to build up much. That means there's a voltage drop across this capacitor, across this resistor, which is going to cause a positive current to go from left to right, and that positive current will turn down here and will deposit positive charge on the top plate of this capacitor. How far does it go? Well, as that positive charge accumulates, it will build up voltage across the capacitor at this point here, because voltage is equal to charge divided by capacitance. Notice that that's going to be self-limiting though, because as the voltage on the capacitor builds up, that lowers the voltage drop across this resistor, thereby lowering the current, positive current I, therefore reducing the rate of increase of positive charge being deposited upon this capacitor. That self-limiting behavior here is characteristic of any phenomenon that can be represented by an exponential increase in voltage. And we'll see that when we do the simulation. How far does it go? Well, if the voltage were 7 volts for a long, long time, let's say many time constants here, the charge on the capacitor would keep building up, but more slowly, until the point at which the voltage on the capacitance was so close to 7 volts that this current would reduce down to a trickle. And that would be the final voltage that this capacitor would eventually stop at. The final voltage would be 7 volts. And you need to remember that for the second half of this lab. But it never gets that high, because before it can reach that point, the voltage from the pulse generator, V sub S, will go into the declining phase, where it will discharge the capacitor, and the voltage will go down to 0 for 550 milliseconds. And when the voltage is 0 on the left side of this resistor, the voltage at the right side will have built up to some significant voltage, and therefore the current I reverses and goes from right to left. And as it goes from right to left, because the arrow has been set going from left to right, the current I will take on a negative sign, and the current I, the positive current I, will go from right to left and will have a negative sign during the discharging period. That will take positive charge off of the capacitor and will move it from right to left. And that will cause the voltage on the capacitor to trend back down towards 0, and its final voltage, if we left it at 0, would be eventually reaching 0 across the capacitor voltage. But it never gets there because we go into the next phase of the pulse generator, which is the charging phase, and that will cause the current now I to reverse back to be positive, and will start building up the charge on the capacitor once again, raising the voltage on the capacitor. Therefore, it rises and falls during each phase of the pulse generator. Now, let's pause briefly while I'll discuss some of the physics of the electricity involved here. Let's fasten your seatbelt. When the positive current is going from left to right during the charging cycle to charge this capacitor, the electrons in the wire and the resistor are actually going in the opposite direction, from right to left, against this arrow. Why? Because electrons carry a negative charge. And you can thank Benjamin Franklin for that. Thanks a lot, Benjamin. So the electrons are going from right to left, and the electrons are leaving the top plate of this capacitor. And when they leave the top plate of the capacitor, that is equivalent to increasing positive charge on the plate of that capacitor. And that's during the charging cycle of the capacitor. During the discharging time of the capacitor, the electrons are actually going in the opposite direction of the positive current flow. The positive current flow was going from right to left. The electrons will be going from left to right and will start accumulating electrons on the top plate of this capacitor, and that is equivalent to reducing the positive charge on the top plate of that capacitor. Now, this is an aside, and basically what you should remember for purposes of this class are all the comments that I made before the pause, because those are the ones that you will use to trace positive current flow and positive charge for this particular class. End of pause. Now let's perform a simulation. To do so, go to the Simulation tab at the top and push the Run button. And after a few seconds, the simulation will be completed. To see the resulting voltages, go to the oscilloscope and double-click on it, and up comes the oscilloscope trace. Along the horizontal is time in seconds, and the vertical is voltage in volts. The blue is the voltage from the pulse generator, and as expected, it stays high for 250 milliseconds at 7 volts, and then drops down to 0 volts for 550 milliseconds before repeating. The green curve is the voltage across the capacitor, and as expected during the charge time it rises, during the discharge time it falls, up and down exponentially. Now what we'd like to do is to analyze one of these rising segments, say this one right here, to see if the values match the values that are expected from the general expression. Now the general expression is that the voltage at any time after the start of the rise is equal to the initial voltage minus the final voltage, e to the minus time, where time is from the beginning of the rise, over the time constant tau, plus the final voltage. That's the general expression. All we need to do is to find the terms in that expression to calculate the voltage after 250 milliseconds. Well, the time constant tau is equal to R, the value of R, times the value of C. R must be in ohms, and capacitance must be in farads, not microfarads, in order to get the time constant in seconds. Please multiply those out and put the value here. The time that we're going to measure the voltage is 250 milliseconds at the end of the rise time. And then the initial voltage we can get going back to the waveforms on the oscilloscope, and using cursor number 1 here with our mouse, we can put it at the beginning voltage or the initial voltage here and read that over under measurements as for cursor number 1 as 0.765 volts. Now that's for my values. Your values are going to give you a different value, so you need to read that for your simulation. And then we know the final voltage is 7 volts. We'll plug that in and calculate the voltage after 250 milliseconds, or 0.25 seconds, and put that value here as the theoretical value. And then we want to measure that. Go back to the oscilloscope trace and grab cursor number 2, the one that's dashed here, and put that at the point where the voltage has risen after 250 milliseconds from the start, and read that voltage over here under cursor number 2. And for my particular values, that's 4.128 seconds. Your value, of course, will be different because you have a different resistor and capacitor values. Put that down for the measured value of V after 250 milliseconds. And then finally, calculate the percent difference between your theoretical value and your measured value. Now, I'll point out that it's not going to be 0% difference because there's going to be two sources of difference here. The first is when you measure the cursors, it's not going to be exact. There'll be some human error when you find the values using those two cursors. But more than that, the resistor and capacitor that we use in this simulation actually mimic real-life resistors and capacitors. And real-life resistors and capacitors don't have the actual exact voltage that's listed on the label. There's some manufacturing tolerance, and that manufacturing tolerance is built into the simulation. And it is actually, going back to the simulation, we can look at the resistor and see that the tolerance is 5%, which is typical of the kind of resistors that you can buy. And it has a Gaussian variation. And the capacitance also has that 5% variation between different samples. Therefore, your percentage difference is going to be in the range of probably 5% or a little less because the resistance and capacitance values change. So mark down and find that percentage difference using this standard equation here. Now to finish up, let's do one further observation of this model. go to the resistor and change its value from 47 kiloohms up to 100 kiloohms, more than double it. Save that. But before you actually run it, try to predict what you think is going to happen to the oscilloscope traces. What's going to happen, do you think, to the minimum value at the end of the declining period here? Will it go up or down compared to before you made the change in the value of the resistance? Will it go up or down? And similarly, try to predict whether the maximum value will go up or down compared to what it was before you made the change. And then actually do the simulation, and on the oscilloscope trace, see whether the minimum value goes up or down, and circle the arrow to show what direction it actually went. You don't have to measure its value, just whether it goes up or down. And the same way with the maximum value. Circle the arrow showing whether it went up or down. And then, based upon your understanding of exponential behavior and time constants, explain why they went the direction they did with just one sentence. And then finally, to finish up, let's print a PDF plot of this oscilloscope trace in order to turn in with the worksheets. There are two ways to do that. We could try to print it right directly from this oscilloscope window, but the problem is that the title can't be changed here, and I would like to change that to a more descriptive title. So to do so, and we'll do this in the last two labs of the semester also, go over to the File tab, pull that down, and print this to the figure window in MATLAB. Here's the figure window, a figure window in MATLAB, and the figure window in MATLAB is much more flexible for modifying this figure before we actually print it. For example, I said I'd like to change that title. Go over to the Insert tab, pull it down to Insert Title, and then that will allow you to change the title to something like RC Circuit. There's my new title. I could change the title on the labels on the axes of the y-axis and the x-axis if I wanted to, but they're okay as they stand. Now we need to save this figure as a .pdf file to turn in with the worksheet. But if we try to directly save it as a PDF file, we run into a quirk based upon Simscape's very large oscilloscope window. Let me show you what would happen if we tried to save it directly. I'll use Print Preview, and you can see that only the center portion of the figure would be saved. The beginning and the end would be lost. There are a few workarounds around this. Let me show you one. Instead of saving it as a PDF file directly, let's save it here as an EPS file. And I will title it RC Circuit and save it to someplace on the computer. And then I will open it up, and notice that when I open it up in Preview, which is a program available on a Macintosh, that it basically has been saved as a PDF file here. If you don't have a Macintosh with Preview, then when you open it up with your particular program, you can export it as a PDF file and save it that way to turn it in. And that will save the entire figure. Now, if for some reason you can't get this to work and you only can save a portion of the figure, turn that in instead, and we'll work on how to get the entire figure saved over the coming week. Well, I hope you found this week's lab to be informative and instructive to help you understand a little bit more about electronic circuits that we'll deal with in this class and later classes in the major. See you next week.